All right, you should see my slides now. So I'm happy to be here talking about my work and how it relates to embodied intelligence. I work on magnetically driven small size devices in robots. And I've been working on making devices like the one shown here, which is a surgical robot. And we're trying to make them much smaller. So we're trying to make end effectors or wristed mechanisms that are single or 2 or 3 millimeters across. And so we want to make them as simple as possible so we can miniaturize them. And so we've been taking this approach where we don't have any computation or intelligence on board the robot itself, but try and deliver that with magnetic fields. So I'm going to tell you over the next 10 minutes about how we program some magnetic response into joints or flexible regions of devices so we can get behaviors that are interesting. So even multiple devices that look the same, we could program them differently to have different responses. And there's other reasons we like to use magnetic fields for powering small-scale devices. We can project magnetic fields over centimeters to maybe meters distance. Magnetic fields penetrate through the human body. We use low-frequency magnetic fields, so the body is transparent to these, and we can exert torques and forces on tiny magnets that we embed into our devices. So we can embed single magnets, and we have some relatively straightforward equations that describe how single magnets respond to a magnetic field and to the shape of the magnetic field. And so using magnetic coils, which can generate magnetic fields in different directions, we can give a few simple inputs to our system, ultimately coil currents, but we're giving a few magnetic inputs, and then we're going to see how individual segments or regions of our robots are going to experience forces and torques, and we're going to get deformations and ultimately motion through the environment or deformation of the device that's interacting with the environment. So this is the kind of intelligence we want to have. A few simple magnetic inputs can drive a device to deform and also move through the environment. So this is just an animation, of course, but shows we want to get these deformations. So this thing starts as a flat sheet. We apply the field and somehow it knows to fold up. So this is sort of the mechanical, how I've been thinking about this mechanical intelligence. This particular folding device consists of a bunch of magnetic regions. That's the black regions connected by flexible hinges, rubber hinges. And each black segment has its magnetic profile is predetermined and programmed into the device. So you see down here a side view, and the red arrows are the magnetization directions of each segment. So this is the magnetic programming, and we use permanent magnet, rare earth magnet materials so that we can lock the magnetization of each segment in, so that when we apply a magnetic field, each of them will respond and close up. So the simplest way to think about these is that each segment will behave like a compass needle. We apply the magnetic field, and each will try to orient to the applied magnetic field. Okay, so one simple input can get each arm to fold up, and we can program each arm to have different responses or the same responses. Now we try and use all the elements of our input, the magnetic field. So this is how we can use how I think about it as 3 elements. We have the strength of the field, its direction, it's a vector, and it has a shape as well. So the strength of the field will open and close different flexible regions on our devices. The direction of the field, the vector field, will orient devices. And then the shape of the field will actually exert magnetic forces, so we can pull devices. And we can do each of these independently. So this is how we think about this as a design process now. We want to impart some behavior to our device. How can we use strength, direction, and shape to get all these different degrees of freedom of control over our device and program the response right into it? Here's an experimental view of one of these grippers going. So you can see we can open and close the gripper on demand. We're also running computer vision here to make this an autonomous type of control manipulation task. We can pull the gripper and move it in 3 dimensions. And this is an untethered version, so this thing is floating around in liquid. Okay, and so we can get these nice responses which respond to those magnetic inputs. And we've been working a lot on how we can generalize this. So any type of deformation or shape of device and motions, joints that we have, how can we program those responses in? And we've been taking one direction we've moved in is a 3D printing approach. We use light to pattern individual pixels of our device. So we cure individual pixels of polymer with magnetic particles. And if we can orient those magnetic particles during the fabrication process and then cure individual pixels with light, we can step through and cure a bunch of pixels where each pixel has its own response programmed in, so that when we apply a magnetic field, we can have the desired response. And of course, we can make the shape whatever we want as well. And we can have magnetic regions and non-magnetic regions to have things like swimming responses. Here you can see one of our devices moving under ultrasound view here through a fluid channel network. We can program things like different gaits to a walking robot. This is just a sheet of material, so it's a flat device. But you see here, every leg has a different magnetic response direction. So you can think about each leg being a little slightly out of phase with its neighbors. So we can program in an alternating gait or a tripod gait that respond to the same magnetic input. So one device may be programmed to be alternating gait, one would be programmed to be tripod gait. You can see here this thing moving as a demonstration of this. We can also do multi-layers to get a little bit more complex responses. You can see folding devices of different geometries. You can actually see the layers of this device printed here. It's quite difficult to develop 3D printed devices using magnetic materials that are embedded. It interferes with the light curing the device. Magnetic materials also make any liquids that we put them into more of a slurry or a paste. So it doesn't flow as well as we'd like. So those are challenges that we continue to work on. And we can make things like capsules, which will open up once we apply a magnetic field. This video will show one of these capsules. We can drive it around. This is on a stomach model in the lab. We can drive this thing around inside the stomach model and apply a magnetic field. This capsule compresses, an air bubble comes out, and it samples liquid. And we're developing versions of these for doing microbiome sampling inside the gastrointestinal tract. But the last example I'm going to tell you about is how we're developing these for making surgical tools. So our vision is to put magnetic coils outside the body. We're working on neurosurgical instruments right now, and then having some response programmed into devices to have dexterous surgical tools. Of course, we need to create magnetic fields over the body. This is our magnetic coil system for doing neurosurgery. Here's me standing next to it with some large magnetic coils. And so unlike the previous devices, which are flexible rubber materials, these ones are made from metal and a little bit larger permanent magnets. And we can embed the response of joints moving, multiple joints, which we can control from the outside. So this is a wireless device. It's just tethered with this rod, which just holds the device in this case. But we can program in different responses like wrist bending and grasping forceps, opening and closing. And we continue to work on those, and we're developing those with surgeon collaborators and trying to do precision control in large forces. Some of our next steps with embedding more intelligence to these devices, we're really interested in looking at interactions between multiple magnetic devices that are close to each other. They exert magnetic fields on each other, and we get these really complex emergent responses, which usually we want to avoid, but we think we can harness these to get a richer set of control inputs to a more complex system, especially if these devices are soft. Their responses can be fantastically complicated, but I think that's a great way to think about designing these as a whole system of devices. Great, I think I'll hand it off here to the next speaker. Thank you.
Thank you very much, Eric. Fascinating work.